Okay, so we are doing more test 3 review, guided practice. Let's go. So number 1, what is the theoretical lowest temperature in both Celsius and Kelvin? Well, in Kelvin, it's what Kelvin's based on, which is just going to be 0 Kelvin. In Celsius is always 273 degrees lower than Kelvin is, so since this is 0, that would be negative 273 degrees Celsius. Fantastic. RTP is room temperature, which means that our temperature is going to be 20 degrees Celsius, and our pressure is going to be 1 atmosphere, which is 1.01 times 10 to the 5th pascals. All right, 3, drawing a heating curve. So when you're looking at a heating curve, all right, let's say that we've got some negative value. So we've got like negative 100, 100, 200. We're looking at water. So with water, if it's under 0 degrees, that means that it's all entirely solid. As you're adding energy to it, its temperature is going to be going up. Okay, once it hits 0, now all that energy is going to be used to transition it from a solid to a liquid. So it's going to be flattening out and remaining the same temperature for that entire section. Okay, now once it's all melted down, once it's a liquid, then that energy being added is going to be used to speed it up again. All right, so you're going to end up with a section where your temperature is increasing again. All right, this is T in degrees Celsius. There we go. So now, once you get up to 100 with water, it boils. So again, you're transitioning between states of matter, and it's going to flatten out again. Now this section where it's flattening out for transitioning from a liquid to a gas is going to be longer than from a solid to a liquid, because you have to get those particles further apart from each other to get it up to a gas. A gas has all those particles free from each other, free to move around. Okay, so you're breaking up more bonds, which means you need more energy to do that. So this section will take more energy. And then your last section, after it's fully turned into a gas, it will again be rising in temperature again. Okay, so basically you're going to have these areas where you've got a slope, where it's one state of matter, and you've got the areas where it's flattened out, staying the same temperature, where you've got 2 states of matter, where it's transitioning from one to the other. Okay, so marking where your KE is increasing, that's going to be each of these. So this is where you've got your change in kinetic energy, because you've got a change in temperature. All right, and we saw from that 1/2 mc squared equals 3 kT over 2, that your temperature and your kinetic energy are directly proportional to each other. Right, so where your temperature is changing, your kinetic energy is changing as well. The points where it's flattened out, that's where you're going to have a change in potential energy inside of it. The reason you're getting a change in potential there is because all your particles have to be pulled further apart. You need to add them more energy to get them to separate. All right, you're getting to separate a little bit when it's going from a solid to a liquid, and a lot when it's going from a liquid to a gas. Okay. Number 4, water has a latent heat of fusion of 3.33 times 10 to the 5th joules per kilogram. How much heat would it take to melt 50 kilograms of ice? All right, so we've got mass, and we're looking at a transition. All right, so it's going from a solid to a liquid. That's that section right there. Okay, so one of the ways we've got to find Q is Cm delta T. Here's the issue. There's no delta T. All right, this is only useful for those sections where it's actually changing temperature. Okay, no change in temperature means we need to instead look at the latent heat formula, which is mass times your specific latent heat. All right, so it's telling we've got a latent heat of 3.33 times 10 to the 5th joules per kilogram. That's L. Your mass is 50 kilograms. Okay, so just plug in and chug and multiply into those two together. All right, 5. It would take 1.13 times 10 to the 8th joules of energy to boil 50 kilograms of water. What is the specific latent heat of vaporization of water? So now we're just looking for L. So L is just going to be Q divided by M. You've got your energy, 1.13 times 10 to the 8th, and you got your mass of 50 there. Okay, so divide it over. All right, now when you compare the energy that you found in 4 to the energy that it told you in 5, it takes a lot more energy to boil that water than it does to melt it. All right, whole reason for that is because you're adding potential energy when you're changing between states of matter. All right, and you need more potential energy to get something to go from a solid to a liquid than a liquid to a gas. Mostly because you're just getting your particles further away from each other. With a liquid, you're breaking some bonds between those molecules, but not nearly as many as going to a gas. With a gas, it all needs to be free to move, so you're going to need a lot more energy. Okay, so now looking at number 7, all of this stuff is all about this graph here. We need to look for the temperatures at each of these points in the cycle for 2 moles of gas. All right, so we've got, for each of these points, you've got a pressure, you've got a volume, you've got 2 moles, and for any ideal gas, we've got that ideal gas constant of 8.134, or 8.314. I'm having a stroke, whichever one's on the sheet. So we're looking for the temperature. All right, so we can find that from the PV equals nRT. Okay, solving that for temperature, we're just going to be dividing that other stuff over. So that temperature is going to be your pressure times your volume divided by your number of moles times your ideal gas constant. Okay, so finding the temperature for each of these points here, you've got a pressure and volume for each of them. Okay, worth noting, if we're looking at going from this one to this one, the volume is staying the same, but we're tripling our pressure. Okay, so that means whatever temperature it is at C, you can just triple it and find your temperature at B. Okay, and then looking from here to here, that's tripling as well. All right, and the pressure's staying the same. So whatever temperature you find at B, just triple it. There's your temperature at A. That's just using gas laws, expediting the process. But you can also use this. Next one, determine the work found or work done for each section in the cycle. Okay, so if we're looking at the work from B to C, remember that work is negative P delta V. Okay, your change in volume is nothing from B to C. If you've got a vertical line, if you've got a isochoric process, no work is done because your volume is remaining constant. Okay, so B to C, no work. All right, now A to B, you've got a change in volume of 1.05 minus 0.35, so that'll get you your delta V, and then just multiply it by the pressure it's at. Okay, now when you're looking at this diagonal section, you've also got your pressure changing, so it's kind of weird. What are you going to do there? Essentially, when you're looking for this work, what you're finding is the area underneath. Okay, so looking for the area here, that's just the area of this rectangle, which would be 1.5 times 10 to the 5th times your difference between these two, right? Your length times your width to find that rectangle. And then looking for this triangle, well, that's length times width divided by 2. Okay, so just find the area underneath this line, and that's your work from C to A. Okay, so looking for work, it's just the area under the line. If you got a vertical line, no work was done. Okay, C, determine the net work for an entire cycle. So there's 2 ways we can do this. You can take, shut up. Any second now. You can take each of your works that you found for part B and just add them all together, right? You've got some positive work here, negative work here, no work here, add them all together. That'll get you your net work. The other way is just find the area of this triangle here, because the positive work that's being done right here going from A to B will be canceled out by the negative work going from C to A. Okay, so whenever you've got an entire cycle that's going all the way around from A to B to C back to A, starting back or going back to its starting point, your work is just whatever area is enclosed. Okay, so it's just the area of that triangle there. Determining the net change or the change in internal energy for each section of the cycle. Okay, so when you're looking for delta U, right? No matter what type of cycle you're looking at, you can use CV and delta T. Right, so CV being your molar heat capacity with a constant volume. For this one, 15.5 joules per mole Kelvin. Your number of moles, we've got 2 moles, and then your change in temperature. You've already found the temperatures for A, B, and C, so for your change in temperature is just going to be your final temperature minus your initial temperature. Your final temperature minus your initial temperature. Your final temperature minus your initial temperature. Okay, and you can always find this using that. Delta U, you can find the same way every time. Okay, now E, the net internal energy for an entire cycle. Now again, you can find that one of 2 ways. You can add together all of your delta U's for each of those sections and add them together, or because it's going back to the same original temperature, looking back at this thing, your change in temperature was 0. Right? Whatever temperature you got for A, it will be back at the same temperature at the end of this process, which means multiplying by 0, your change in internal energy for a full cycle is 0 joules. Okay, so if you've ever got a full cycle ending up back at the point that you were at, your change in internal energy is 0. Okay, now F, determine the heat released / absorbed for each section of the cycle. All right, now depending on which type of process we're looking at, we're going to have to think about this in different ways. Okay, so going from A to B, all right, that is a constant pressure. All right, that means that you can find this using CP and delta T, right? You can only use a CP thing when you've got a constant pressure, All right, going from B to C, you've now got a constant volume. So Q is C, oh my God, Q equals Q. Q equals CV and delta T. Okay? And then going from C to A, well, that isn't a constant anything. No constant pressure, no constant volume, so we're going to have to think about it the other way. All right, your change in internal energy is your heat plus your work. All right, you've already found the work being done going from C to A. You've already found your change in internal energy going from C to A. So Q is just going to be delta U going from C to A minus that work. Okay? Now G, the net heat absorbed in the cycle. Okay? Determine net heat absorbed cycle for an entire, I forgot some words, for an entire cycle. Okay, so your heat absorbed is just all of your positive ones added together. Okay, so any positive heats that you got from part F, just add those together. H, your heat released. Any negative heats you got, add those together. One sec. Okay, so now for I, looking for the net heat for an entire cycle. Two ways you can do that. That net heat, you can either do all your Q pluses plus all your Q minuses, all your heat absorbed plus all your heat released. Just add all that together to find your net heat. The other way, because your total change in internal energy for a full cycle is always zero, that means that your heat and your work have to be equal and opposite. Okay, so you already found your net work, which means you can just flip the sign on that thing. There you go, you found Q. Okay, so take whatever you found for your net work, whatever question that was, and just stick a negative on it and you're done with your day. J, the efficiency of a cycle. All right, so efficiency is your output over your input. Your output is the work that you've done, your net work. Your input is the amount of heat that was added to the gas. Okay, so just take whatever you found for your sum of all your positive heats, whatever you had for G, and just divide that into your net work, and you're good to go. Next one. Wait, that was J. That is a J. There we go. K and L. Type of process is A to B. All right, so A to B, you've got a constant pressure. That means you're looking at an isobaric. So barometers measure pressure. So baric for barometers. B to C, isovolumetric or isochoric, or the way that Evan said that he remembered it. So to exercise your core, you do pull-ups. This thing moves vertically. Choric, core, vertically for your graph and your motion on a pull-up. I don't know if it works for him. Go for it. So B to C, you've got a isochoric process. Number 8, in isothermal. Isothermal, you've got a constant temperature. So if you're graphing that, that's basically going to be Boyle's law, where you've got that inverse curve. As your pressure goes up, your volume goes down, and vice versa. Number 9, adiabatic. Very similar looking graph, a little bit steeper. Okay, with adiabatic, basically you're making it transfer between pressure and volume and temperature and all that stuff inside of a vacuum. So there is no environment for it to transfer heat to or from. Okay, so you'll have no heat transfer, which means that your delta U is always just going to be equal to your work. All right, so no heat transfer for adiabatic is basically what I'm getting at there. And that is more test 3 review. We're good to go. Good luck on the test tomorrow. See y'all later.